Right.
Okay?
Exactly.
Just like, stay in your lane. Just, I got this. Okay.
Right.
So, I'm just delighted to announce that tens of thousands of people flood the streets for reasons other than Con Ed digging holes. I went to the police department and I said, why don't we organize this and block off the streets? And, we need authorization from the mayor's office. It's like, it's going to happen anyway.
Yeah.
It's not like people are going to flood the streets only with your permission. They're doing it anyway. So I'm alerting you of this. And so I got the runaround. I'm very disappointed. Maybe by now they're going to figure it out. But anyway, back to Stonehenge. So there are these 56 circles that surround the stones. And Gerald Hawkins, in the early days of scientific computing, put these coordinates into his computer, and he found that there's a configuration of these circles that enable you to predict eclipses. Eclipses recur on what's called a Saros timescale. And a Saros is the time it takes the sun and the moon to realign in a configuration that would give you another eclipse. Because the moon's orbit around the Earth is tipped relative to Earth's orbit around the sun. What that means is you don't get a lunar eclipse every full moon and a solar eclipse every new moon. If that was all lined up, you get eclipses twice a month.
Right.
But we only get them every couple of, every 2.5 years or so. And so it's only when the geometry lines up. And there are families of eclipses that repeat every 18.6 years. And it's called a lunar Saros. That's what it's called. Okay? So now, watch what happens. If you take 18.6 and multiply it by 3, you get 56 holes. You get to 56. So he viewed these holes as a mechanism to get some handle on the prediction of eclipses, which would have granted these ancient peoples some understanding of the motions of the heavenly bodies that no one would ever give them credit for.
Absolutely.
Okay. Later, decades later, there's been some re-questioning as to whether this was actually an eclipse predictor, but no one is questioning the alignment of the heel stone of the summer solstice. Anyhow, it's still there. It's a national monument. It's protected. It's still in the middle of a farm field, but everybody's in agreement, and there are tours that go there. You can't touch the stones anymore. When I was there, you could climb on the stones. That's how old I am.
Nice.
That's
kind of cool. Back in my day, we didn't give a about Stonehenge.
No.
Well, we climbed all over it. We sat there. We drank on it. Some people actually made love on it. It was wonderful.
Carved my initials?
I carved my initials in Stonehenge.
Do all old men on the porch sound like that?
I remember when rocks were more than rocks, and you could actually go to Stonehenge and put your name in it. It's worth the days.
Oh, by the way, there are people who don't believe or recognize that ancient peoples had the same brains as we do. I mean, they're human beings. They can be as clever or as stupid. They just have less technology. So you can ask, how long does it take to find bluestone and drag it, dozens of miles to a location? It takes long if you don't have tractors and trucks, but it doesn't take forever.
No.
Okay? And so they knew about the wheel. You could roll on records show that Chuck could not have his fingers. Neither could I. I close one eye, put my hands back, and I miss it by an inch. So what we did was, it's a method of triangulation. You have two angles of view. So in other words, you have one sight line that intersects. It can be anywhere along the sight line. If you have two sight lines, those two sight lines intersect at a single point. Right? And geometrically, you can know exactly the distance to that object using this method. Let's do that with the Earth's orbit. Because consider, the farther away something is, the less useful the separation of your eyes will be. Think about it, right? If something is a mile away, you can just stare at it. It's just far, right? Stars are far. So, how do you help out the baseline of what would be your eye on your eye sockets for something that's that far away? You use the entire orbit of the Earth around. Wow. Ain't that something? That's so like one eye. It is. One eye is Earth in June. Right. And the other eye is Earth in December.
Right. So it's because they're in two different spots. It's your left eye and your right eye, and then you have a sight line, and then you look 2 points where they come together.
Sight lines. Okay.
Wow.
And so here the way this works is.
My God, that is so simple and so smart.
So you get the nearby stars, and it turns out they're far, but they're close enough for this method to work. Here's what you do. You take a picture of that star against the background star. Okay? And it's going to be sitting in front of some pattern. Then you wait 6 months, you take that same picture again, and your sight line on that star has changed, and now it's sitting slightly in front of a different pattern of stars. Very slightly. That corresponds to an angle. That angle, okay, is one part of that triangle, and we have the base of that triangle, which is the diameter of Earth's orbit, right? Because it's not the radius, it's the full diameter. That's the diameter between your two eyes. You do the geometry of this bottom. We know the distance from Earth to the sun. Right? You need that because that's one of the legs of this triangle. Before we knew the distance from Earth to the sun, you could not successfully apply this method because you'd be missing one of the dimensions. Let's say you had the wrong measurement here. That wrong measurement would eke its way into these other measurements and propagate through all of your estimates for the distances to stars in your neighborhood.
So before we knew the sun was 93 million miles away, the answer to this question was, woo, you don't even want to know.
I never thought of giving that answer to questions. So that's why it's a ladder, because any error at the base level of this would propagate to all other levels. Okay, so now we get the distance to the nearby stars. Okay, now we hope, we made sure one of those stars is like the sun. Okay, now we know the luminosity of the sun by orbiting the thing, and luminosity is how much energy it's giving off. So, if I know how much energy it's giving off, then I start putting it farther and farther away from me. It gets dimmer, doesn't it? Of course, yeah. If I know what its intrinsic luminosity is, then I can calculate the rate at which it gets dimmer as it moves away from me. It's called the inverse square law of light. So, if I find another star like the sun, I get spectroscopically, I get to say, that star is just like
our sun, right?
And therefore, I believe I know its luminosity because I know the sun's luminosity.
Right.
Based on that, I can now give you the distance to that star with a simple formula.
So then, I guess you change it because there are a lot of different stars with different luminosities and some things that aren't even stars.
Well, right. So that gets me the distance to stars that look like the sun.
Right.
Okay? But if I get a triangulated distance to a star that's not like the sun,
like a brown dwarf or something,
like a brown dwarf or any other red giant or whatever, and I get the triangulated distance, now I find another star like that, and then I can apply the same method. Recently, there's a satellite called Gaia. Okay, Google it. It is a specially tuned satellite designed to get this triangulated distance method to 1 billion stars. Rather than just the few. Yeah, that's because it's above Earth's atmosphere. It can measure the tiniest angles with very high directly correlates with the luminosity of the star. And again, all you have to do is know what is the luminosity? It's the wattage stamped on the light bulb. Okay? And so if you know that there's another light bulb with the same wattage, but it looks much dimmer, it's because it's farther away. Because you otherwise can't see distance in the universe. The fact that you can't see distance led legions and generations of people to think that the stars were just points of light on the inside of a dome, on the surface of a dome, leaving them to think that constellations were real things. Okay? But no, they're scattered in space. And since any other angle of view on them, they look completely different. They're not real things. They're completely in your head. Okay? So stars are scattered in space. So once you knew this, Hubble found one of these variable stars in the Andromeda Nebula. And he measured its pulsation rate, deduced the luminosity, then calculated its distance, and it was a holy moment. This nebula is not in the Milky Way. It is way beyond the limits of the Milky Way. In fact, it's an entire other galaxy. The Andromeda Nebula overnight became the Andromeda Galaxy.
Oh, snap.
Yes, all of these we didn't know these were just nebulae. We just called them nebulae, the fuzzy spiral thing. They were just nebulae. Why would we think there's anything other than our own system? There's got a little bit of our ego playing out there. Okay, there's another island universe out there, an island galaxy. There it was, and then that opened up the entire universe, and that happened between 1926 and 1929. We're in the centennial decade of discovering how big the universe really is because of a distance method to determine the distance to this kind of variable star discovered by Henrietta Leavitt in the Harvard College Observatory. Then, once he got the distance to Andromeda, he could get distances to other galaxies with methods similar, and then he found out that galaxies are receding from us. And the farther away the galaxy is, the faster it's moving away. Well, if that's an actual relationship, then you don't need to separately know the distance. You just have to measure how fast it's moving away, which you can do using the Doppler shift. Just measure the speed moving away from us, and you put it in the Hubble equation, and out pops the distance. Wow. So that is the ultimate. That's the highest rung of the distance ladder, what's called the redshift of the object, which was based ultimately on variable stars traceable to nearby galaxies, traceable in our galaxy, traceable to the triangulation method, traceable all the way back to just looking at stereoscopically with your eyes.
Are there any theories out there about dark matter